Okay, any questions or issues from the homework before we get started on new content? Yes?
I just wasn't here last week, so I don't know if you had like a policy on decimals. Some of my answers were like a little bit off because of the decimals.
I'm assuming everybody knows how to round correctly, so if the number after the spot you're rounding to is 5 or higher, you go up. That's how that goes. So rule of thumb, 3 or 4 decimals is probably good, but sometimes round more or less depending on what situations. But I'd say 3 decimals, 3 or 4 decimals. It doesn't, something around there. Okay. You said you weren't here last week, but you got the class website and everything. Okay, good. Good. Okay. Any other questions? Okay. Next week we will have a quiz, and we'll start at 7 o'clock for the quiz. You'll have about half an hour, so get here on time, and then that's that. You're allowed to have a note card, 3x5 note card. Don't make it any bigger than that, and make sure you have your own. You can't share note cards or stuff during the quiz. Details of the quiz, what you need to know, is covered on today's homework page, or this week's homework page. I have information about the quiz there. It will cover last week and this week's content. Okay. Just one sheet, front and back. Pretty straightforward. I think 30 points possible. There might be like 4 or 5 questions. Okay, so everything was good. Standard deviation, that makes sense? Yes?
Yeah, I emailed you a question, you didn't respond.
That was about the molars, is that?
Was
Okay, I just responded 20 minutes ago or something. Okay. So one of the questions said we took molar measurements from 36 specimens. Does that mean we have 36 measurements or 72 if everybody has 2 molars or whatever? The answer is, I guess it depends how the person gathered data. I just read it as 1 molar, 1 measurement per person, or 1 measurement not per person, but per sample or per subject specimen. Maybe they took an average of the 2, I don't know. Or maybe they took 2 measurements per specimen, or 2 data points. It depends on how they set up, but 36 or 72, so yeah. Okay. Any other questions? Yes?
Yeah, can we just talk about why those measurements are continuous and not discrete?
Which measurements?
For the molars?
For the molars?
Yeah.
Because they are measured in millimeters, and technically, I don't know how big, I don't know what size of mammal this is, but let's say the molar could be, is like this big, okay? Maybe it's 12 millimeters, maybe it's 13 millimeters. Is it possible to be 12.5 millimeters? Sure, okay? Depending on how accurate or how precise our measuring device is, we could get 12.5, we could get 12.6. Any value is quite possible. If we had very accurate measuring devices, we might measure the molar to be 12.567 millimeters or something like that. Okay. There's nothing about molars themselves that say they only come in size 12 millimeter or 13 millimeters and nothing in between, so it'd be continuous. Okay. Whereas if we were to ask how many fingers does someone have, that's going to be discrete. You can either have 5 fingers on your hand or 4 fingers. You can't have 4.5, or you have to you'd have to quantify something there. Okay, so you can only have a whole number. Well, I guess maybe fingers isn't the best example, but if we're talking about number of children, you can only have 3 children or 4 children or 5 children. Something you cannot have 3.2 children. So that would be discrete. Just want to make sure that we've got a good grasp on spread, measures of spread. So we have the range and the IQR and standard deviation as measures of dispersion or spread. And those concepts are okay. Creation of a box plot, also okay. Okay, you guys are nodding your head or silent, so I'm going to assume that it means you guys are okay, and we will move on. Again, if you have questions or issues, don't hesitate to ask. Okay, so today we are moving on into Chapter 3, which covers probability. So last week we talked about data and just describing data using numeric summaries, okay? Data, describing data and using numeric summaries. Or statistics to describe data sets. So that include things like describing the center, with the mean and the median, and describing spread or dispersion, with the range, IQR, and standard deviation. So this gives an idea of where, the center gives us an idea of where our data is located, or how large typical values are. And the spread gives us an idea of whether the data set, the numbers in our data set are similar to one another, or if they are, if they vary wildly from one data point to another. Okay. Okay, and so that was last week. This week we're covering probability, which feels very different. We're going to learn like rules of probability along with random variables and things of that nature. And in the future, we're going to tie data and probability. So probability is all about how likely or unlikely unknown outcomes are. Okay, so we have something that's unknown, we can talk about the probability of a certain outcome. And meanwhile, on the other hand, we have data, which is information that's been recorded and measured. Okay, so when we bring these two together, okay, we've talked about our understanding of unknown outcomes, and we use that to understand data which has already been recorded. Then we can do statistical inference, and this will be in the future. Okay. So sometimes we have to learn probability, and depending on the student, this may or may not be a well-liked chapter. But it's important because our understanding for the statistical inference depends on our understanding of probability. So anyway, let's talk about probability. Allows us to express or quantify how likely or unlikely or unlikely the outcome of an event would be. So it only makes sense to talk about probabilities for events with unknown outcomes or events of uncertainty. For uncertain events or events unknown outcomes. We have this concept of randomness. Randomness describes, can be used for, used to describe the outcome of an event where we cannot predict the outcome. Okay, so randomness, we cannot predict the outcome of a random event. But that does not mean we cannot understand it. Okay? Also, random is different from arbitrary. Okay. And when we're in our case, when we're talking about random events, these random events could be described using the rules of probability. Okay. Scarred this chalkboard. Okay, in our class we take a classical view to statistics. Okay, classical view of statistics, which depends on a classical view of probability. Okay, classical view of probability. Spills over into our view view of statistics. And what I mean by this is we take on, when probability was first being studied, this is the view that they used. Okay, so if you've taken physics, you probably first learn Newtonian physics, right? And force equals mass times acceleration, these types of things. But then you learn later on, I don't know, that quantum mechanics and general relativity and all of these things kind of change the Newtonian view of physics. But for our day-to-day purposes, Newtonian physics works pretty well enough, okay? And so classical statistics, or the classical view of probability works very well, and it's just, maybe in the last few decades or so, another view of statistics, or another view of probability has emerged, and that would be the Bayesian view of probability. I shouldn't say it has emerged. It's been around for a while, but has gained more popularity because of modern computational power. But this classical view of probability, it's tried and true, and it works, and we will have, we can do a lot with it, okay? But if you decide to study more statistics or more probability or things like that, you might come across another, quote, more modern view of probability, okay? So the classical view of probability is also known as the Frequentist View. Okay. It's based on frequencies. And it all comes down to this question of, if I say, when I flip a coin and I ask what's the probability that it lands on heads, you would say 50%. Okay, you'd say the probability that the coin lands on heads is 50%. Okay, or 0.5. A coin flip. So we're talking about a fair coin, that a coin flip lands on heads. Is 0.5, okay, or 50%. Okay, so it all comes down to the question of, well, what does it mean that the probability is 0.5 or 50%. What does it mean when we say that the probability a coin lands heads is 50%? What does that mean?
Keep flipping it over and over and over again. Half of the time you're probably going to get heads and half the time on tails.
Okay, so if I flip it 100 times, will I necessarily get 50 heads and 50 tails?
No, but it'll be close.
Okay, it'll be close. Okay. Well, that's a starting point. Are there any, yes?
There's only one or two ways in which
Okay. There are only one of two ways that it can land, but it's not necessarily, that doesn't necessarily mean the probability is going to be 50%, okay? If I try to shoot a basket, okay, we're playing basketball, and if I try to shoot a basket from half court, okay, there's only one of two possibilities. It either goes in the basket or it doesn't. Does that mean I have a 50% chance of making the basket? No, okay? Especially me, half court, probability is going to be lower than 50%. So even though there's only two possibilities, or two possible outcomes, that in of itself doesn't necessarily mean the probability is 50%, 0.5. Okay, so when we talk about the frequentist view of probability, when we say that the probability that the outcome, or that a coin lands heads, is 0.5, we are talking about the long-run relative frequency. Okay, so our definition of probability comes from the idea long run relative frequency? So for example, let's say part of your homework assignment was to go home and flip coins a bunch of times. I'm not going to assign this, okay? But let's say I said, I told everybody, flip the coin 10 times. Okay. What kind of results might we see when someone flips a coin 10 times? We might get 5 heads and 5 tails. 5 heads, 5 tails. And that would correspond to 50% heads. Okay. But I could also see 4 heads, 6 tails. And that would correspond to 60% heads.
40%.
I'm sorry, 40% heads. And I could see a variety of responses, okay? Could I see 70% heads after 10 coin flips? Sure. 70%. I could also see 30%, 60%. These are all quite possible, okay? Even 10% heads or 100% heads is possible, not very likely, but it's possible, okay? Okay. But, you know, most of our answers, we would expect most of the students to get 50%, 40%, 60%, and maybe some 30 and some 70%. Okay. All right, what if I have, instead of flipping the coin 10 times, I have you flip the coin 100 times? Okay, what kind of responses will I see here? Okay, so I might see 50 heads, 50 tails, which corresponds to 50% heads. Okay. What else might I see?
51, 49.
51 heads, okay, 49. So that would be 51% heads. I could see, you know, 47 heads, things like that. What about 40% heads? How often will I see 40% heads? Okay, not very often, but it's possible. Okay, 40% heads. What about 30% heads?
Very unlikely.
So, okay, so over here, 40% heads seems like pretty likely, right? This seems like we expect it to happen frequently. And this will be 30% heads, probably not frequently, but it'll happen occasionally. Okay, if everybody here flipped the coin. Okay. Meanwhile, when we're flipping the coin 100 times, okay, these ones seem likely. 40% heads seems to happen rarely. Or happen, yeah, I'll put rarely. And 30% heads would seem to happen incredibly infrequently, okay? So I'll write very infrequent. Okay, and if I bump it up to flip the coin 1,000 times, okay, again, now we're expecting a more narrow range of likely percentage heads. Okay, we would so the percent heads. We expect to be very close 50%, okay? Seeing 40% heads means what? Means we got 400 heads and 600 tails. Okay, and this seems to be very, very, very unlikely, right? After 1,000 coin flips. And seeing 30% heads almost seems unfathomable after 1,000 coin flips. So far, so good? Okay, so the frequentist view comes from this long-run relative frequency. What we're saying is that after millions or billions of coin flips, okay, millions or billions of, I should not just say coin flips, but random trials, the overall relative frequency will be very close to our theoretic probability. And the long-run relative frequency is the notion that if we were to do this an infinite number of times, which is physically impossible for us, because infinity is unreachable, but that is the notion, okay? So it's the idea that if we were to flip a coin an infinite number of times, then half the time it would land heads, okay? But of course, we will not flip it an infinite number of times, and after a finite number of coin flips, we might have the relative frequency to be very close to 50%, but of course it will not be exactly so. This brings us to the notion of the law of large numbers, but first I should define what we have, the empirical probability, which is really just the relative frequency based on our data, okay? So if we flip the coin 1,000 times and observe 493 heads, then our empirical probability would be 493 out of 1,000, or 0.493. Okay. The theoretic probability, on the other hand, is the probability as determined by the rules of probability. Okay. By the rules or axioms probability. And that says something like the probability that a coin lands heads is 0.5. And what I just illustrated with, or tried to illustrate with the coin flips, flipping them 10 times versus 100 times versus 1,000 times, is an illustration of what we call the law of large numbers. The law of large numbers states that as you increase the number of trials, we expect that the empirical probability gets closer to the theoretic probability. So after 10 coin flips, it's possible to have 5 heads and 5 tails, and you'd have exactly 50% heads. And so therefore, it's not possible to get any closer than that in the future. But after 10 coin flips, it's also very possible to have only 40% heads, or to have 60% heads, or something quite different from 50% heads. Whereas after 1,000 coin flips or 1,000,000 coin flips, we would expect the empirical probability that we observe to be much closer to the theoretic probability than we could if we only flipped it a few times. Is this concept okay? All right, so this is how casinos stay in business, because all of their games are set up in a way that the casino has a slight edge in probability. And so even though an individual may, quote, beat the house, and they walk away with winnings, because they are anticipating so many people to go through and gamble, that in the long run, because they're increasing the number of trials of different people playing games, they can expect to stay in the positive in terms of making money. But of course, there may be times when their players get quote-unquote lucky, and their short-term winnings are positive. And actually the casino would probably like that, because they also understand the psychology of gambling and how that brings people back. So anyway, that is, this is, again, classical view of probability. Okay, let's talk about maybe some notation here. And, maybe some of the rules, okay? So if we have some event, okay, we could have a particular outcome. So for some outcome, A, we say the probability of A occurring that A happens. Okay, so we might say the outcome, or this might also be known as an event. Okay, so for some event A or outcome A, we say that the probability that A happens is written as the probability of A is equal to some number. Okay, this could also be written P of A. Okay, so the book sticks in an R, but then other texts do not. These are equivalent. Okay, is equal to the probability of A. Any probability, the probability of A, is always going to be between 0 and 1. Okay, so if you have a probability, it must be between the numbers 0 and 1. If the probability of A is equal to 0, it means A never happens. Okay? And this is a literal never happens, okay? Not in our day-to-day speech. use the word never as in many times hyperbolic senses, where it's like, I don't know, they never spell my name correctly, okay, at Starbucks or whatever, you know? But that's not true. Sometimes it does. It's not a never, okay? But this is a literal never. It's meaning it's impossible. It never actually happens. And on the other hand, probability A equals 1 means A always happens. Again, a literal and not hyperbolic use of the word. Always happens. We have what we call complements of events. Complement. So complement here is spelled with an E. So it's not a nice thing you say, but it's what completes the picture. Okay, so the complement of A is the event or outcome where A does not happen. Okay. So we can write the complement of A as not A, or A complement, or A prime. Okay, so basically all of these mean that A did not happen. So if we say the probability that the coin lands heads, if A is the probability that the coin lands, or is the outcome that the coin lands heads, what would be the complement of A?
The outcome is tails.
Okay, you guys say tails, but it's actually not heads, okay? So if A is heads, lands heads, a complement is lands, or does not land heads, okay? Okay. In most scenarios, we would say does not land heads means it lands tails, but technically, I suppose when I throw it up in the air, an eagle could swoop down and eat it, and that would be included in does not land heads, or it rolls under the table and I can't reach it, or something, you know. Everything else for where it does not land heads is included in A, the complement, okay? But we might just simplify the world and say, well, it's either going to land heads or land tails, and if that doesn't happen, we ignore those outcomes and just limit ourselves to these two outcomes only. And in that case, you would have the complement of A being that it lands tails. Okay. So in that case, the probability of the complement, so probability of not A, is equal to 1 minus the probability of A. So that means the probability of A plus the probability of not A equals 1. So either one of those two things will happen. Either A happens or it doesn't happen, and that covers every single possibility ever. So those are complements there. We have cover something called conditional probability. Okay. So let's say we have another event B. Okay, so we have event A and event B. Okay. Then we have something that says the probability of B given A. Okay, and we write this as the probability of B vertical bar A, and we just read this as the probability of B given A. Okay, and this is the probability that B happens if we know that A has happened. Okay, so this could be something like all right, so here's a silly situation, okay? Let's say you decide what you're going to do tomorrow by writing out possible activities on a slip of paper, and you list out the different things you want to do, you throw them into a hat, and you draw it out of a bag, okay? All right, so if it's a sunny day, the things you're going to write on your pieces of paper will be go to beach, go hiking, stay home and watch TV. All right. And if it's a rainy day, or if it's not sunny, we'll just say if it's not sunny, so rainy or cloudy or whatever. If it's not sunny, you're only willing to stay home and watch TV, or go to the movies. Okay? So, all of these things, if it's a sunny day, we would write each of these things on a piece of paper, we would throw it in the bucket, and then we would reach in. And each one has an equal chance of being selected. Is that right? Okay, so we would say the probability of going to the beach, if it's a sunny day, is equal to 1 out of 3. 1 out of 3. So if it's a sunny day, I'm going to write 3 things, one thing on 3 different pieces of paper, and I'm going to throw it into the bucket. I'm going to reach in and decide what to do that way. Okay? What's the probability of watching TV on a sunny day? Also 1 out of 3. So, is that okay? So if it's a sunny day, I also have a 1 out of 3 chance that I'm going to watch TV. Okay? on the other hand, what is the probability that I watch TV on a not sunny day? 1 out of 2. Is that okay? Okay, good. What if I ask, what's the probability, if I don't know what the weather is like tomorrow, what's the probability that I just end up watching TV? Okay, so before you guys try to answer this, I'm going to tell you, you can't answer this question without knowing the forecast, okay? If we're living in